Please, use the microphone.
Is this on? Yep. Okay. So the way we're going to do this is that for the next few hours, we will be in an interactive session. What that means is you need to pause me, you need to interrupt me, and you need to ask me questions about things that are not working for you. I have a piece of paper and a pen here to take notes, because I'm sure there are questions that you have that I don't have answers to, and I want to make sure that those answers are taken care of. So I will go back to my home, and I will make sure I have your email address to answer those questions. So please ask questions for what you want to do. The other trend that's going to happen is we will go from less technical to more technical. Towards the end, I will start showing you code. So please bear with me as we go from less technical. Well, this is pretty technical, but we will go towards code. So more and more, as the hour progresses, we'll go towards code. The agenda for today is I want to give you a very high-level overview of how to think about building LLM applications, applications that have language model at their core. And then the way to think about this, back in the day when you had internet and mobile phones were just coming, I was recently employed by Motorola at that time, a very, very hot company. And when we thought about the internet, we thought about big screens. And the mobile devices really changed the paradigm. And then there was this thing called mobile first. Everybody wanted to build applications that were mobile first. We are now entering an era where everybody wants to build application that is AI first. And I want to impress on you some of the tactics people are using when they think about AI first application, where AI, the LLMs, are the core of the application themselves. So I will go through this a little bit, and I will work with you on a particular use case that I'm currently working. This is a customer that I have in India. It's a very, very large-scale project. So I want to work with you and go through that project plan and understand and get feedback from you around how are you thinking about the project that you want to do. What are the similarities of the project that you have with the project that I'm explaining? What are the differences? How would you do this differently? We'll go through aspects of project management. We'll go through aspects of planning. We'll go through aspects of how much data would you need. All of this is not written down. It's an interactive session. That's why, again, it's customer data. I cannot share the customer data with you. But the next best thing I can do is provide a live example that is a project that is in the works right now that's going to get deployed in October timeframe to hundreds of millions of users. So the motivation for this is, and I said I was going to do less PowerPoint and more technical stuff, and this is what I mean, right? This is how an engineer works. So the application is this, that the user story is there is an input text coming in a non-English language, okay? The input text is right now in one of the Indic languages. Nepali is one of the Indic languages. There are 22 official languages in India. Nepali is one of them. And it goes like, Mero paniko bill ta yo mahina 700 po ayo, kina? Okay? That's a text. It could be spoken, it could be written. Now, there are a lot of complications just with that input, because when people type in Nepali, they will type using the Roman letters because that's what is in the keyboard. However, they are not going to find all the variant in the Roman letters to write those sentences that I have. In fact, I'm so bad at typing Nepali, it took me half an hour just to write those 2 sentences, right? And that's one of the challenges that you see in low-resource languages is it's not only that there are not enough text tokens, it's, people don't know how to write, and you have to support them. You have to use other modalities of input to enable people to use. A lot of people in India are illiterate. They didn't ever learn how to read and write, and we need to support them. So there is an input that talks about water bill being sort of over what there was average for last 6 months, right? That's the query. They had an average water bill for the last 6 months. Now this month, the water bill is high. What's going on? That's the user query. Now, on the response side, what is expected from the LLM application, and this is where the AI in the central part of the application comes in, is we are saying, like, there's an output that makes sense to the human when they read the output. It is a natural response in the language of their choice on what is it that they expected. So in the output, it says, "Tapaiको घरको मिटरले यो महिना 6000 लिटर पानी खपत भएको छ." So what it's saying is, in the last 6 months, you've been using average of this many liters of water, and this month you used much more water, and hence your bill is higher. Now imagine how you would build an AI system that can do that kind of reasoning and talk to the user about the problems that they are having. How would you build a system like that? And that's the next 3 hours is we'll try to discover how would you tease apart the project aspect of how this project, the particular application will be built. So I'll come back to this notepad and we'll talk more about this. We'll go through sprint 1 and we'll go through the longer project planning. And then after that is done, we will go into the code. So that's sort of the 3 phases. I'll do the PowerPoint first, very high level, get you an understanding of what is important conceptually, and then dive into this, the specific user story that I'm focused on for the next few months. And then we'll transition and look at the code base that supports some of these things. Again, all of these things are work in production, but I wanted to give you a live example of something that's in the works that has not been fully built yet, and give you the idea of the complexity and the challenges around building language model applications. Let me pause here and do my first test of whether this is going to be an interactive session. Can you raise your hand if you're awake and if you're listening to me? Yes. Yeah, please go ahead. Slower. Thank you, Marcy. This was, Guillermo yesterday said, speak slowly, you speak too fast. I apologize, I will try to speak slowly. Yes. Yes. So the input in this particular application, it is a government-focused application. It is citizen services. So imagine you are a water utility. In that water utility, you have customers paying bills. Now there is a customer who is unhappy with the current month's bill, and they think, look, I've been paying this much money for the last 6 months, every month, for my water. This month I'm paying much more. What is going on? That is the user query. And it is in a natural language of their choice. There are 22 languages, again, in India that are official. We need to support majority of them. In this particular project, we are focused on only 2 languages, and I'll explain why, right? But the complexity is when the customer comes to us or to a application builder. In this particular case, there is another partner we are working with who is actually building the application. I'm just sitting there and looking at over their shoulders. But they have specific requirements. They have user requirements like my user cannot read more than 200 words. Okay? So that particular user requirement has implications to the AI application, because the way you train the AI application to converse is going to be dependent on what the user knows and what the user can benefit from. Okay. All right. Now let me do the PowerPoint and we'll come back to this. So I'm going to start like yesterday as AI as software 2.0. I cannot say this enough. People yet have not understood that this is a new way of writing software. This is not a sort of incremental improvement. This is a fundamental shift that is happening in how we write software. I'll give you one example. I'm working in parallel in another project to build a radar system that is AI enabled. And I started over Christmas. I wrote my first neural network over Christmas break, and then I've been doing it. And more, what I've found in that project, I look at the code commits that I have. More and more, the code that I'm writing is coming out of LLMs. Right? That is software 1.0 that is coming out of LLMs. And I believe, right now about 40% of the code I produce is coming out of LLMs. I believe that's going to go to 60% by the end of this year. Next year is going to be 70, 80% of the code that I write that goes into production is going to come out of LLMs. That is still software 1.0. You are still using traditional Python programming, C++ programming to write your programs. Software 2.0, as we sort of saw yesterday, cannot be written using software 1.0, right? These are the software 2.0 we talked about yesterday, right? On the left, there's a black and white image that my first project in NVIDIA colorize it, right? On the right, you have this chocolate cake from Jan LeCun explaining the important aspects of what what a machine learning system does. Both of these, I'm going to assume you know this. I'm going to very quickly explain because I see new faces here from yesterday. On the left-hand side, we are trying to take a black and white image to a color image. Let me explain just how difficult this is from a traditional programming point of view. The guy's shirt is seen as white. Okay? That could have been pink, it could have been blue, it could have been maroon, because when you take things to black and white, they will be like that. The siding in the walls, on the outside walls, right now I've painted green. I could have painted that. Blue, I could have painted that. Yellow, red. There is almost a collapse. There is a lack of information, right, going in terms of how do I colorize this. And when you do this for a whole movie, from frame to frame, the neural network will go from, a green wall to a red wall to a blue wall, because the neural network doesn't know. I have to put additional constraints into it. Again, from a programming point of view, I cannot program that. I cannot say, make all the walls green. It has to learn internally that some walls are green, and when I have a different viewpoint of the wall, it also has to be green. It cannot be a different color. That internal representation, the machine has to learn itself. We cannot program that in. If we are allowed and if we are able to program that in, that would be software 2.0. If the machine has to learn it, software 1.0. If the machine has to learn it, it would be software 2.0. Right? So a learning system is a software 2.0 system. And then the sort of important part on the right-hand side is there is this idea of how do you teach a machine. And the way to teach a machine is like a way to teach a dog, right? You have to give it rewards, and you have to tell it good dog, bad dog. And that is the reinforcement part. However, that's a very small sliver of what needs to be done, right? Those are the cherry in the cake. That's a very, very small part. A majority of the cake itself, right, the gnomes of the cake, the millions of bits per sample, is the unsupervised data. It's just random data that you pluck out from the internet. We were talking about this yesterday over dinner around chemistry data. There's a lot of out-of-distribution chemical data, right? Chemistry is very, very weird and strange, and you can get a lot of out-of-distribution chemicals. However, we tend to filter out those out-of-distribution stuff to clean our data. What this suggests is we shouldn't clean our data for the first pass. We should use all the data that we have in an unsupervised manner to learn really good features that will capture some of the out-of-distribution features that is needed for good performance. Let me go to the next one and now talk a little bit about, in the application that you are building, you have, yes, please. Yes, please. Yeah, for me, in the project that I'm working on, the radar project, the AI sort of enablement of radar, I expect by the end of this year about 50, 60% of the code, and by end of next year, 70, 80% of the code that I write for that project would be driven by LLMs.
And suppose that these statistics are correct, let's say they're going to expand to other repositories and also other codes. Do you think that even in the future, if most of the codes will be written by LLMs, so it's going to be easy to train the LLMs to learn the code, or no? Because if I have all of the codes generated by LLMs, supposedly, all of these codes are in domain of the LLMs. So it will be easier to train them, or
That's a very interesting question, right? In terms of token distribution, and this is, please correct me if I'm wrong, but this is asking, can we use tokens synthesized from the LLMs to train the LLMs again, right? Is it going to extend the generalizability of the LLMs? And the answer is yes. Specifically in non-English languages, the majority of the tokens that you'll put in your LLM training is going to be synthetic. It is going to be generated by a LLM. So, and there are like pros and cons to it. Yes?
Yeah, but I think we still have the human in the loop process. Yeah, the LLMs is writing new code, but humans are validating and seeing. It's not as automatic as the machines take control of everything, and we are outside.
That's why I asked it ought to be easier, not totally replaceable by the machine. Because one of the things I have been studying LLMs a lot in software engineering. Now the main thing is that usually all of these Git repositories, they're all created by human beings. So the LLMs have been trained with human-generated code. So what happens is most of this code, in fact, would be generated by LLMs. This would be easier now. This is what I question, but yes, definitely.
Yeah.
Humans still need to be there.
Yeah, for me, the sort of, again, we can, yeah, there is a human element to it, right? When I initially started generating code, I had to build a full Python application to help me write code in another project, right? So I had a project called Coder that helped me write code for Radar, right? And that was, a year and a half ago. Now the LLMs are smart enough, and this is one of the things we'll talk about, is as the capability of the language model increases, the things that needed human supervision goes down. And human supervision is still needed, but in different areas, right? So, and this trend is year over year, the kind of things I used to do human in the loop had changed. I'm no longer looking at small doc strings or small function calls in terms of editing. I'm more looking at, is it doing the right planning? Is it sort of, because when I give it a task, it will produce 400 lines of code. And I want those 400 lines of code in that prediction to be as correct as possible because I want to minimize the human time spent in that. But the way to get there has been not like, for me, it has been building my own infrastructure to do coding, but on the other side, using this more and more powerful model. The Gemini model, for example, the latest Gemini model, the latest Nemotron model that we have that supports reasoning, those are really good for things like project planning. I can give it a task to say, I am building a neural network for doing radar processing. The TX signals phase is going to change in this way. And it will use physics reasoning. It will use neural network reasoning to come up with, oh, you need this attention mechanism in this manner that is different than how you do it in language. That insight would never have come if I had worked alone. That insight has come because now I can work with the AI, with the LLM, and investigate that different axis of innovation. All right. So when building LLM application, and let's say you build an LLM application and you give it to your customer, the first thing they're going to do is they're going to test these two things. They're going to test knowledge capability, and they're going to test language fluency. And failure in any of these is going to be a failure for the application. You need really fluent language capability for customer-facing and consumer-facing applications. Less so if you are working on very constrained environment. Let's say you are building an LLM application for doctors. They really don't care as much about language fluency, as long as you get the technical terms right. They don't care if the buts and the ands are in the right places. However, consumers really care if the language fluency is good. And in fact, in their mind, fluency is not what's sort of authoritative English or authoritative language. It's more slang, it's more local dialect, it's nuances in the local language itself. And when we talk about a country like India, you can have the same language spoken in two different states and have quite different dialects. And those dialects can be very important. Thank you. Slow. So from an LLM point of view, right, how do we understand and test these two things, right? Knowledge capability and language fluency. And there are a couple of papers that hint what is it, right? How do we test it? The first paper is the window into latent space. I'm sure a lot of you have seen it, in which you take a embedding, again, there's a technical sort of topic, and I will explain what an embedding is later in the talk. You take an embedding and you look at the vector distance between embeddings. And here, it's fairly straightforward to understand. There is man and woman in the x-axis. Okay, it's a gender axis, if you can think of that way. There is man and there is woman. And then in the y-axis, there is king. And then in the z-axis, what we are trying to find is where is that correspondence to king? Okay? And we can find this vector that will take a king to a queen. Okay, so think about vector arithmetic. Now you can do vector arithmetic. You can say king minus man plus woman equals queen. Okay? And that's sort of the window into latent space, just by looking at embedding distances between different vectors, is really interesting to think about, because it tells us something inherently what language models are learning. They are learning this correlation in our language to understand semantic concepts. Man and woman corresponding to king and queen is a semantic concept. You cannot find that syntactically. Right? It's a semantic concept, and the language model, the embedding system, has figured that out. And these embedding systems are fairly small. These embedding systems might be 150, 200 million parameters, and even those small embedding systems can find semantics in the languages that we use. The second diagram here is a sentence translation, and it also gives us insights about the way the language models work. And this is a neural translation. You can see different lines in the graph. In the x-axis, you have length of the sentence. How long is the sentence you are trying to translate? It goes from 0 to 60. So you have up to 60 tokens, so to speak, that you can translate. In the y-axis, you have accuracy of translation. There's a crude accuracy called blue score. Everybody uses it. It's effective enough. And that's the y-axis. And you can see these different sort of lines. The thing that stands out from these lines is you can see as the sentence length increases, the translation accuracy decreases. Okay, so there is some correlation. We talked about having this semantic knowledge within the embedding system. There is some correlation that the semantic knowledge decreases as the task becomes harder. Okay, as the sentence length grows, the semantic knowledge decreases. And that is going to be important when you build a language application. You have to think about the hardness, the difficulty of the use cases that you are trying to tackle. And not all problems are going to be equally easy or equally hard. And we can get some insights from here around, there's going to be a performance degradation. Now, the way to overcome those performance degradation is you want to move up to different curves, right? And the moving up to different curves, the lowest curve is a particular algorithm called RNN encoder with 30 million parameters. Right above that, the same algorithm with 50 million parameters. Okay, let me pause here. There are a bunch of side conversations going. I want to get into the side conversations. Questions? Yeah?
Minha pergunta é se as IAs podem piorar com o tempo, como elas vão começar a ser muito usadas, né? Principalmente o que ele falou sobre o uso de LLMs, né? Eu queria saber se elas podem piorar a qualidade, mesmo com muito treino.
He's asking if the LLMs can lose quality with time.
Okay. So the question is, if we were to train LLMs using LLM input, is the quality going to degrade? The answer is not necessarily. You can produce tokens in such a way that the quality does not degrade. There are issues with it. In fact, as I said before, most language models nowadays are trained on synthetic data. And in fact, the next sort of evolution of language models they're going to be trained online on their own tokens, on the synthetic data that they produce. They'll train themselves. So it's almost like we are in a phase where we can imagine things, and based on these imaginations, we can change the model, right? The model can imagine a particular scenario, and it can change its own weights based on the performance in that scenario, given the current weights. Right? So there's a bunch of interesting research happening, but the general answer is, if you train a model with synthetic tokens, it really doesn't really mean it will collapse. Okay? Other questions? Okay. So I was explaining this middle diagram, and this is going to be important when you think about the size of the model that you use in your LLM application. And the reason, and hence I'm showing all of these things, right? You want to understand the semantic knowledge, which is the first diagram. There is going to be some inherent semantic knowledge that the language model will learn. You want to understand where that semantic knowledge starts failing, which is the second diagram, because you'll see this performance drop in some axis, right? In this case, the difficulty is sentence length. In your use case, it will be different. In the use case that I will show you, the difficulty is something else, right? And then there are techniques of improving the performance, and the two techniques, number one technique is you just increase the size of the model. When you go from a 30 million parameter to a 50 million parameter, you can immediately see this bump up. That's the last two lines, the bottom two lines as that. And then the second thing you could do is you can change the architecture of the algorithm itself. So going from an encoder to a search RNN, even the 30 million parameter is a significant bump. So when you are hitting in your LLM application performance degradation, when you are hitting these issues, there are two things you could do. Well, one is you can scale up your LLM, right? You can just make it bigger. Rather than using a 3 billion parameter model, you use a 7 billion parameter model, or you use a 70 billion parameter model. That's one way you can solve the problem. The second way you can solve the problem is you can change the algorithm. Rather than using GPT 3.5, go to GPT-4. Rather than using Llama 2.1, go to Llama 3. Use Llama Nemotron, our latest model, right? Those are algorithmic changes that also gives you performance increase and protects against this semantic slippage that you see. Okay? Now the third one is quite interesting, and this is more anecdotal. I don't have a lot of evidence to back this up, which is smaller models, and when RNN 30, RNN 50, right? Those are the sizes of the model. Smaller models, at least in the non-English language model case, they want to, mostly they want to translate, right? So if I ask a small Llama 3.1 model a bunch of questions in Nepali, rather than trying to answer the question that I'm asking, it will try to reply to me in Nepali, because most of its energy, it seems like, goes in that language fluency versus the knowledge that it can give back to me. And I have seen this not only with Llama models, but also with reasoning models. Quen is a reasoning model. And I asked, again, this is all anecdotal evidence. I have a very small sample of 50 or so Nepali questions and a small evaluation set of 50 answers. And when I do this, I found that a lot of the smaller models, they are useful. The people love them because they are really fast, right? In applications, you want models to go fast. However, the language capability, fluency comes at the cost of knowledge capability. Let me pause here and see if you have more questions. Yes.
the languages, they are very different, especially in the number of characters. And how can these LLMs, non-English LLMs, can vary in size based on the language they're using, they are being trained on?
So the input to the language model, right, it can be in different characters. So typically in English, we use Roman literals, right? In Hindi and other Indic languages, there's multiple scripts. Hindi uses Devanagari script. However, that's not the thing that gets fed into the language model. There's an intermediate pre-processing step that takes English text into what we call tokens. These are vectors, right? So, and then that happens for all languages. If I take Devanagari script, Hindi text, I will have to tokenize it. I will have to convert that into a vector. I cannot directly feed the ASCII values of those of the characters into the language model. So there's this intermediate step, and that intermediate step usually normalizes so that the language model only sees the same length vector all the time. Does that answer your question? Yes.
But still, going from this logic, since a language has so many more characters than another one, in principle, you would think that the vectorization space where you tokenize would have to be different. So if you take a model architecture that is best suited for, say, English, and try to use the same architecture but train another model in another language that has way more characters, in principle, the model would have less knowledge of the language itself.
That is correct. And in the sort of later half of this talk, we will go through some of the tokenization method that you can use to mitigate this effect. Right, so I think what he brought up, and thank you for bringing this up. If you have a fixed token length, let's say you have a vector that is fixed, and you have a pre-trained model that works on that fixed vector. If you bring in other tokens, for example, Nepali tokens to a Llama model, whose majority of the tokens are Roman, right? In fact, the Llama model has less than 0.003% of Indic languages, right? It's really poor in that language. So the Devanagari script and those things are still already tokenized, but the distribution of those tokens is really small in the original data set. So there are approaches of how you could modify the distribution of the tokens. You can either change the weighting of the tokens themselves, that's one approach. You can extend the token length, that's another approach. You can have prefixes and things like those, right? And then we have some code that I can go through around how is it that we extend, for example, the token, or how do we retrain the tokenizer so it's more suitable to your local language. Typically, when you build a LLM application, you would start with existing stuff, and we'll go through some project planning that I've done for this project. And then at some point, when you want that big performance bump, then you would retrain your tokenizer. It's too risky to mess up the tokenizer for simple applications. It's just not worth it. Right? There are so many other complexities in building the LLM application, you don't want to touch the tokenizer initially. If you want that big performance boost towards the end, you can do it, but not initially. Okay. Other questions? All right. So the middle diagram suggested that if we increase the size of the model, the performance increases. At least in sentence translation, that was the effect. Right? That's what the last slide showed. And here is some more interesting validation of that idea. We call this train time scaling. Pedro yesterday did a presentation in which we had 3 different scaling laws. This is one of the first one. And what this says is on the x-axis, the first diagram, it is looking at how many parameters do you have? How big is the model, right? And this is non-linear scale. This is exponential scale in the x-axis. In the y-axis, you have loss. Loss is a proxy to the metric that you really want to measure. Loss is a very poor proxy, but that's all we got. So we're going to use loss here. And what you see is as the size of the model increases, a lot of neural network, like LSTM, this is long short-term memory, a couple of different variants of it with different number of layers, and then the transformer, right? Those are two architects that are represented here. Again, I talked about algorithms, right, as one of the impact in terms of how do you increase the performance. So LSTM and transformer, two different algorithms across different sizes of the model. What we see here is the performance keeps on improving for transformers. There is almost this linear line down a logarithmic scale for transformers. So what that indicates is if you can train larger and larger models, the performance increases, okay? And it's a very simple fact, and that's why you see 200 megawatt data centers coming online because of this one simple diagram. And this has been validated multiple times across different architectures. Anything that has transformers, or attention, I should be very specific, anything that has attention demonstrate this capability that the loss function goes down as the model size increases. The second diagram that you see, the performance versus step, right? A corollary to that is the loss function also goes down as you increase more compute. Let's say you take the same parameter neural network, which is you pick a place in the x-axis and go up, right? So let's pick 10 to the 7, right? And you go up, make a vertical line up. You can see these different curves. And the difference between all these curves is just the compute budget, okay? So same network, same data set, put more compute, and it performs better. Okay, very, very interesting finding, and this has huge implication for your application. Because if you are going after an application that you want really to perform well in certain areas, there are a couple of things you could do. You can increase the size of the model, which has other unintended consequences. For example, it's going to be more expensive and it's going to be slower, right? Or you could increase the amount of compute. You can train it for longer, which also has other unintended consequences. For example, catastrophic forgetting and less, loss of generalization. But both of these techniques are used to great effect to build LLM applications. Okay. The third diagram is essentially trying to figure out, is there an optimal? Given a particular compute budget, let's say you have 4 DGX, and you want to build a LLM to do something, is there an optimal size of LLM? And if you are pre-training, there seems like there is, right? And this is called a Chinchilling scaling law. And this has been proven again and again in terms of how much, given a compute budget and given a data set, what kind of model do you want? Okay. And then the last one is not only does this hold for individual models, this also seems to hold for a collection, an aggregation of models, which is, is shown as a mixture of experts. Okay. So a very, very interesting finding that will have implications for how you think about your LLM application. The core of your LLM application is going to be the LLM, and these things will impact the LLM and the choice of parameter size, amount of training that you do, amount of data that you collect. All of that is going to be impacted by this. Yes?
Thank you. In that third graph image, there is this, this is really a linear function against your budget, against the number of parameters.
Right. So it's linear, but if you look at the scale on the x-axis, right, it is going orders of magnitude, right? So from that point of view, it is linear in terms of as you add more data and compute, the performance increases, right? And it looks like it increases sort of in a correlated way.
Oh,
that's the strongest statement I can say. There's a strong correlation between size of the model and the compute budget and performance, right? And the optimality is where the correlation is the strongest.
Yes, and another question is, in this paper, may I have a way or a function that I can calculate if I have this budget to buy this 1 million flops.
Right.
So I must to have a model with X number of parameters. You have how to calculate
Yes.
this in that source?
Yeah. So it's not linear. Yeah, it's a log scale. But what you're asking is, do we have a formula? They present a formula. The caveat is a lot of companies, if you think about the budget that they have, let's say you have $10 million, okay? You have to split that $10 million across data and compute. Algorithm is usually free because PhDs, we don't pay them much. Sorry, guys, right? So algorithm is usually free. So what that means is you can use the compute, either for compute, the budget for either for compute or data. What Meta did in the last iteration of their 3.2 models was rather than spending more on data, because data was very expensive for them, they spent more on compute and they took advantage of the third diagram. Right? So there's, again, from an optimality point of view, it would have been optimal for them to build a larger model, but because of the cost involved in training a larger model, they said, okay, I'm just gonna not collect more data, because larger models mean you need more data. Right? They said, I'm going to stop collecting data and I'm going to train the same model for longer to get the impact that you see in the second diagram.
Okay. Right. Makes sense.
Okay. Other questions? So we know now a couple of things about how these transformer models work and how we can sort of take advantage of them when building our LLM application. So specifically now, I'm going to more and more towards, we are trying to do non-English language models. What are other things we need to know? So on the left-hand side, this is how a language model works. It works at a token scale, right? So it produces one word or a word fragment at a time. In this case, I have 1, 2, and then I want it to predict the last or the next token in this case, right? And what you see is the language model is going to give me a probability distribution across the tokens that I should be looking at, or it will want to predict, right? So 1, 2, and then the most natural thing, about 40%, with 40% sort of probability, cumulative probability, it says it should be 3. With about 16, 17%, it says it should be an and. And that gives you a very good insight about how language models work and how it's going to impact your application. Imagine this was a customer typing something in, right? The customer is typing 1, 2, something. Now, when the language model wants to understand that customer, it's going to want to say, oh, I expect a 3 over there with 40% probability. And if it doesn't see a 3, then you are now out of distribution. Okay? You are now slightly out of distribution from where you were before, where the language model wants to do. And that's where the real work happens, is as you go small, slight out of distribution, the language model comes to a token that makes sense to a human. Okay? Now, on the right-hand side, what I'm showing here is the same chart I showed you before, but now specifically for things that are interesting to an LLM application. Things that are interesting to an LLM application. Can it comprehend what it is reading? Let's say you are building a retrieval augmented generation application, RAG application. A RAG application, it will have a bunch of text, and LLM has to understand that text, interpret that text, and then give you a response based on that interpreted text. So reading comprehension, does the capability of reading comprehension increase with the size of the model? And the answer is yes. Second one, translation. Does the capability of the language model increase with the size? And the answer is yes. Right? So task after task after task, we see that the performance is increasing as the model size increases. Now the natural question for an application builder is, okay, this is very clear. Let me just use the largest model that is around because I'm going to get the best performance from my application. And that is true. However, the flip side to using the largest model you can have is it is expensive. It is expensive to train, and it is expensive to inference. Not only that, it is also slower because it's a larger model. Imagine having to do matrix multiplication against 1 billion numbers versus a 70 billion numbers, right? That's what parameters are. These are numbers that need to be matrix multiplied. And that's essentially what's happening here. When you want to do matrix multiplication, 1 billion numbers for a 1 billion parameter model, it's going to go fast, but the performance is going to be low. So in your application, as you are thinking about how much budget do I need, how many people do I need, how much data I need to collect, this is the kind of thing you should be thinking about, is what kind of performance do I need, and for that, what size of model do I need? Okay? So the way you take advantage of this is similar to summarization, similar to translation. You can have other tasks as next token prediction task. And in this case, we are doing protein folding as a next token prediction task. Okay? There is an open source NVIDIA library called BioNeMo that allows you to think about protein folding as a next token prediction task. Let me relate this with the last slide. I showed you reading comprehension, translation, summarization, question answering. Each of those seem like language tasks, and you are happy with it. You didn't complain. Now I'm going to show you, in fact, this is a language task as well. It's not human language, but it's a language nonetheless. And language models have the same behavior. As you increase the size of the model on this particular project, the performance increases. The protein folding gets better. I'll show you another example where you can specify a game like Doom. Right? Those are old enough who played Doom. Right? This is a game, and what they did is they converted each frame of the game into ASCII characters. Okay? And there is a game engine that's driving this. There's an external game engine that's driving this. But the input to the neural network is just ASCII characters. It's not frames. It's ASCII characters that represent the frame, somehow represent the frame. And the LLM is asked to play a game. The data set for doing this is very small. It's around 2,000 examples, right? Less than 2,000 examples. With less than 2,000 examples of gameplay, the LLM is now able to play a new game of Doom, okay? The sort of core of this is you need to specify the task that you are after as a next token prediction task. And again, let me tie it back. Reading comprehension, translation, summarization, question answering. These are language tasks. We are happy with these language tasks. Now I'm going to expand the definition of language task into protein folding, into playing Doom, and into doing software development. Okay? On the left-hand side, you have a agentic system completely driven by LLMs to do software development. There is a QA role, there is a program manager, there is a software engineer. There are multiple roles here, and they collaborate with each other. They talk to each other, and then they solve this problem of creating software. So here you are specifying the task of software development somehow as a next token prediction task. Okay? On the right-hand side, you have chemistry. This is a talk came out of PNLL where they are designing the prompt to search across a very large search space of catalyst. Okay? And this is doing things like reasoning. The user says, I want, what are the top 3 catalysts for the reverse water-gas reaction? And let's think step by step. And the answer is the response from the system. It gives a response. And then it evaluates its response and says, oh, I made a mistake. I'm going to go down a different search path. So each of these circles that you see is a reasoning or is an output of the LLM. And it is going and looking at the output and going down that hierarchy more and more to find a catalyst that satisfies all the user's requirement. Again, this is a reformulation of the catalyst sort of discovery task as a language task, okay? To emphasize this more, I'm going to go back and I'm going to show you this again, okay? The main theme here is you have a language model. It is a tool. If you can convert your use case, if you can convert your problem domain into next token prediction task, you can do things like reading comprehension, translation, summarization, question answering, protein folding, playing games, doing software development or chemistry. I hope these examples impresses on you that the use case that you have to think about how do I convert that into a next token prediction task? How do I convert that into a task that an LLM can solve, where we can use the power of compute, increasing the model size or doing more compute to get better results? Let me pause here and take questions. I feel like this is the central theme. If you do not understand this theme, you will not be able to build great LLM application, because this is the core of the LLM application. Okay, questions? And feel free to ask in Portuguese. We have a lot of people here who can translate.
Good job. They're understanding everything.
Okay, awesome. I need my application done in 2 months. I might come to you guys. So as we work through our application, right, how do we know we are making progress? Let's say you found a way to reformulate whatever you are doing, whatever the use case you have, as a LLM problem. Now, you want to make progress, and you want to measure progress. And this is where evaluation comes in. And here, like in regular software engineering, like in Software 1.0, test-driven development is the name of the game. Okay. In the first line that I show you, it's essentially human effort. On the left-hand side, you have human evaluation, which is the most expensive kind of evaluation, but it is also the best evaluation you can get. If I go to India and can allow the people in the field, in the streets, to test my application and give me feedback around language fluency and knowledge capability, those are the two things I'm looking for, then I can do a lot of good for my application. I can evolve my application by taking their feedback. But it is a very expensive process. I have to go to India. I have to meet people in the street. I have to, have them sign some paperwork. Otherwise, PII and all that stuff, right? So it's a very expensive process, but it is the gold standard of evaluating how well your application is working. On the right-hand side, you have automated verification, things like chemistry or things like math, where you can write a verifier that can accurately tell you whether something is correct or incorrect. That is the automated verification. Now, you would love to do automated verification, but it's very, very hard to create a verifier. In the case that I started with, where I was trying to figure out why my water bill was so high, it's almost impossible to write a verifier, because the user can ask any query, and a lot of responses would satisfy the user query. There's no one single right answer to the user query. So automated verifiers require certain characteristics on the problem that a lot of LLM applications do not have. So more and more, we have to go towards human evaluation. And there are mechanisms now in which you can figure out how do you do this human evaluation at a cheaper rate. Okay, maybe human evaluation becomes a proxy, and you can use more automated things. So we'll talk about some of those ideas later in the talk. Okay. The way you evaluate LLMs, regardless of whether you're doing it in an automated fashion or using humans, is through certain axes. Spider charts are very, very popular in LLM world. And what they essentially do is you look at as orthogonal axes of evaluation as you can find. Let me sort of explain what that means. So in my particular application, I need to do a couple of things. I need to make sure that the user's sort of query I can understand, right? So I might have an axis of evaluation in whether I did understand the question the user was asking or not. I can have another axis of evaluation in which I say, I need to retrieve something from the database, and I need to make sure that my retrieval is correct. Because remember, I showed you that I spent this much water in the last 6 months. Right? That is in a database somewhere. So I retrieve that information, and I sort of evaluate the retrieval on that. And that could be another accuracy of retrieval, could be another axis of evaluation. Language fluency can be axis of evaluation. You can have linguists come and say, okay, is this the colloquial language people speak? And you can have an axis of evaluation around language fluency. In fact, I would recommend when you are working on your LLM application, you have 6 to 8 evaluation axes that you work with the product manager of the application who will have insights on the users, and you meticulously design evaluation criteria around those evaluation axes. In fact, this is usually the first step in any LLM project, is thinking about how we're going to evaluate. Because even before you start, if you don't have an idea of measuring progress, then you're not going to progress. Okay. Now, in domain-specific things, right, for example, in the middle, there's Bloomberg GPT. This is a finance LLM, right, LLM tuned to do finance well. You can have very, very domain-specific ground truth that you can use to evaluate. In the medical domain, similarly, you can have medical ground truth about cataract surgery, for example. This is something I worked on, right? Can you, if the language model does not understand the vocabulary, then its language fluency will be low. If it doesn't understand mechanics of how cataract surgery works, its knowledge capability will be low. But essentially, the thing that you have to think about is the more generalized your domain, the more broad your application, the more you have to have this domain-specific evaluation, and the more difficult it becomes. It's much easier to create an LLM application that just works for water utilities and thus just does customer service than to create a generalized, all utility. I can do power, and I can do electricity, I can do gas. That is much harder. And it just makes sense because the evaluation of those things just gets more and more complicated. And then finally, on the last section, we have a lot of evaluation tools that are open source. Not only NVIDIA, but others in the ecosystem have built evaluation tools. There are evaluation data sets that you can use. And there are capabilities, for example, annotation of evaluation data. There are companies who provide annotation services for you to create evaluation data set. Right? So it's becoming a rich ecosystem of players to help you evaluate the application as you are building it. Questions? All right. So a block diagram of what we are trying to do, right? So we want to get to this end state, application in local language. That's the goal that I have, and this is something that we have to deliver by October. Okay? Started this project a month ago, so we are 4 weeks into the project. We got a couple of sprints to go, but the final goal is I go to India, I hand over a mobile phone to a person in the street, and they can ask a question, either typing or voice, and they get here. Right? That's the application in local language. Now that application on the back end is going to connect to a LLM service. Let's just call it a broad LLM service, right? That backend LLM service is going to probably be agentic in some way. It will have to do, for example, database search, because it will have to know how many liters of water I used in the last 6 months. It might have to do some web search. It might have to look at the customer record, right? A bunch of capabilities that an agent would have. In this case, we have a very, very simple agentic framework in mind where we are doing tool calling, essentially SQL, and then we have a web search to look at any information that we can find in the web. So 2 tools, that's the agent. And there are 3 boxes there now. The retriever is where you want to go and get the SQL data. okay, or a structured data. That's the retriever part. The guardrails is to make sure that the language model just doesn't answer things that are out of domain for it. If people want to ask about gas utility versus water utility, our language model has to say, I'm sorry, I cannot help you with that. I'm trained only for water. That is the guardrail. It makes sure that it doesn't go off topic. If you want to talk politics, this will instantly shut down. India is a very politically active environment, so you don't want any government stuff to be politics, right? And finally, the last one, NIM, is essentially our way of doing inference. The NIM and all of these things come on the left-hand side, which is the building, right? So on the right-hand side, you have the deploying side. This is the thing that you want to deploy. On the left-hand side, this is how you build it. You need sovereign data. This is data that is local to your country, have cultural context, has history, knows about electricity and water regulations and things like those, right? So that is the sovereign data. It has to be curated because a lot of data, again, it may not be clean. It might have duplicate information. It might have contradictory information. It might have incomplete information. So there's some manual and automated curation involved. You also have curated internet data, right? So this might be in Portuguese, it might be in English, it might be in other languages where you get the knowledge to the LLM because your LLM in the sovereign data may not have the knowledge necessary to perform the task. And we've seen this in finance, in healthcare. It's almost impossible to get good healthcare data in Nepali. It just doesn't exist because we didn't have doctors 200 years ago. We don't have a rich history and tradition of doing modern medicine. So all of those tokens exist in non-Nepali languages, non-Hindi languages. So we either have to translate it or we have to use English data. So this is the curated internet data that's coming in. And the translator name can translate it. We can put it as English. And those set becomes your pre-training data, like localized foundation model pre-training data. You take that data, put it through the NEMO framework, and you get a embedding model, which is what we talked about at the beginning of this, and a base model, which is a Llama model or a Gemini model, whatever you want to call that. So on the top side, that is building a Portuguese or a Hindi model. Right? That's a generalist Portuguese, Hindi, non-English language model. That's like the OpenAI, Llama models. That's the top half. On the bottom half, you have a use case specific data. In my case, I want to have hundreds of thousands of user queries and user assistant responses as the use case data. And we can do multiple sort of fine-tuning of the base model, of the model that already has language fluency, and inject this use case knowledge into that model. And that will give me a trained, adapted model, which I can take to inference, which is the NIM that you see on the right-hand side. Okay. Any questions on this diagram? This is most likely your first sort of high-level architecture. Yeah, please.
I don't know if you're going to take more time talking about the first one, the NEMO curator, if you use ontologies or taxonomies, or if you have inference on that one already or not. Are you going to explore that more afterwards? If you do, you don't need to answer right now. You just say.
Do you have a specific question? I will talk more about NEMO curator, but if you have a specific question, I can answer now.
I'm curious about doing inference in that part there. Do you already do it?
Yes, so for synthetic data creation, we have to do inference.
Of course, yes.
Right, and there are two ways you can do inference in this area. One is for the filtering itself, right? And the filtering can be just, I don't want to see this text, or it can be rewriting. A lot of times, for example, when I get text from Wikipedia, it is not in the colloquial language that I want. It is in a very academic language. And that will reduce my language fluency. So there might be rewriting that I do of the Wikipedia data into Wikipedia colloquial, so to speak. And that part, you can do inference. And that's also part of synthetic data. The translation is an inference step.
And regarding ontologies, do you have repositories specifically for that? Because we have some work done on ontologies in Portuguese.
Right.
And I'm wondering if what can be easily reused in NEMI Curator or not.
We do have capability to support different ontologies. Primarily, ontologies are used to make sure that class balance is there. Right? So I think the biggest value that I personally find in having a good ontology and mapping my raw data to the ontology is to ensure that I have the class balance. In a lot of cases, if you are just doing the bottom part, you probably don't care as much about the class balance. If you're pre-training your model, if you're training a model from scratch, that's where ontology becomes very important to make sure that you have representation across all the different things that you're interested in, and that's where you create ontology.
Thank you.
Other questions? Okay. So, given the last few slides, now I'm going to sort of go to the challenge that we have in application development, right? Given the last few slides, the left-hand side, the building localized foundation model, we know is going to be easy for us if we choose a large model and if we have a lot of compute budget, right? We just, like, whatever data we have, given fixed amount of data, if we have a larger model, from the last few slides, training, scaling laws, and things like those, we know a larger model is preferred. On the right-hand side, we know a smaller model is preferred. Okay? Does that make sense? There is a dichotomy in which the task for us to train the model to do this use case very well, I would love to have a large model on the left-hand side because I can train it faster, it is going to sort of learn things faster, it just has more knowledge, it will learn the language faster as well, right? Fluency, capability, knowledge capability, both of them will go faster for the bigger model. However, on the right-hand side, if I have a big model, it is very expensive. It is expensive to compute, and it's also latency is very high. A small model can do things in milliseconds or hundreds of milliseconds. The large model might take seconds. So that's the dichotomy that we have. There are strategies around it. I will go in the last slide a little bit about what is the strategy. But when you are building your application, LLM application, my recommendation is to first focus on the left-hand side. Make sure you have a working application on the left-hand side. Okay? Make sure the LLM, if it has to be big, it's okay. Go with the big LLM. Make sure that the ideas that you have, the evaluation that you have, works well with large model. Because if it doesn't work with a large model, it will not work with a small model. And that's what we've seen in the last few slides, right? So let's say you want to do something and you say, oh, I need to do inference and I need really fast inference. My latency is in less than 30 milliseconds and I can only have a billion parameter model for that. If you start there for your use case, it's going to be very, very tough because there are so many other things that impact the use case sort of evaluations on the small model side that you don't know how to fix it. However, if you start with a really large model, let's say you use a 70B parameter model and you get success with only 5,000 examples within 1 week. Great, now you have proof of life. It works somewhere, right? Existence is proof. And then you can start going down, okay, now I need to take this 70B parameter model down to a 1 billion parameter model, right? That's the next step, but you've at least proved that your use case can be done. A lot of times I see customers struggling because they start on the hardest problem first. They start with a 1 billion parameter model, they want to do a low resource language use case that is out of domain for most language models, and that's where they fail. Questions?
We have 5 to 10 minutes to have a break.
2 more slides.
Okay.
Yeah.
No.
Okay, so let's say you've sort of started with a big model, right, or a small model, and you have a agent that's doing this. You have a bunch of tools, right? You have SQL, you have web search. In our case, we're going to do those two. We might also have a calculator, and then we have this specialized agent that can do this water utility use case that I talked about. Now, the interesting thing here is this loop that you see here, that's the first part you want to get to, right? With a 70B parameter model, get to that first part without this underlying loop, okay? So take a large model, take your use case, create an evaluation set, and get to this stage, okay? Phase one of your project is getting to this stage with whatever you have, right? With the largest model, make the problem the easiest you can, and get to this stage. Once you are at that stage, then now you can start really going after and solving the customer use case, right, in the way the customer wants it solved. So as the customer uses it, this is, you know, in lean startup, right, when they do startups, what they teach us is you have to get customer feedback on a daily or even hourly basis. So if we were able to successfully build this part, I would deploy this to test users right away, even with a 70B parameter model. The feedback I'll get is it's slow, right? It's too slow for me. It's not, you know, it might be expensive, things like that. That's the feedback I get. What I don't want to get feedback on is it does not perform well. That's not the feedback I want at this stage. At this stage, I want to say, okay, for a limited number of question answer sessions, I'm getting good results. Once that happens, then I can really start scaling the number of users. So in my plan, we have about 5 users that we're going to onboard as soon as we get this thing working. Okay, with the largest model we can get, with about 2,000 examples, we're going to get this deployed to 5 users. And then we start this loop. We call this a data loop, in which we get the logs that comes out of this conversation from these 5 users, and we mine those logs for insights. We mine those logs to make the application better. We mine these logs to make the data set more rich and the model smaller. Okay? And this is an iterative process. The more users use our system, the more data that we have. And the more data that we have, the smaller the model I can get into, the more performance I can get from the same size model. Okay. And last one, this is a very complicated diagram. I apologize. But the distinction I was making before between training and inference, right? In the training world, when you want to train, you want larger models that are going to train fast, that already have the knowledge capability, language fluency. That's what you want. In inference, you want a small model that can run really fast. And the way to bridge that gap is what we call distillation. Okay? It's essentially taking a neural network and taking some of its parameters, throwing them away, creating a bunch of synthetic data, as you can see here, and then retraining a smaller model with as much and equal capability as the bigger model. And this is usually the last step. If you get to it and you want to scale to hundreds of millions of people, this is the last step you would do. After that loop that you had before, you'd go here. Questions?
Just a comment. Pessoal, não sei se vocês lembram da minha apresentação ontem, quando eu falei da família de modelos open source da NVIDIA, Llama, Animotron. Aqui é o esquema como eles foram treinados, tá? Fazendo uma otimização ali da arquitetura, de pruning, né, para ter uma arquitetura mais, para ter uma eficiência maior na hora da inferência, né? E depois distillation do Llama, e aí tem todo o passo a passo até chegar ao final ali do Llama Animotron com raciocínio, né? Com 253 bilhões de parâmetros, tá? Em português.
Yeah, I think I heard what you said. So we are going from 405 billion parameter to 253 billion parameter. This model performs better in all regards than the original Llama 3.1. Okay, so this is the power, and this hopefully answers some of the question we had around synthetic data and things like this, right? This is using a lot of synthetic data, and yet it performs better than the original trainer or the producer of the synthetic data. So the curation of the data is really important, and this is an example of that. The distillation methods and code, the code is available for you. It's a fairly complex thing to distill a model, a language model. But we have the code. If you're interested in really doing it, we will help you do it. But even without distilling, the general methodology and framework that you have is you start with a big model, you solve your problem, you create a data loop, and once you have the data loop, you start thinking about, okay, how do I make sure that my inference is cost effective? Okay? Questions? And I believe that's my last slide. No. So let's take a break.
Yes.
Yeah.
Bom, pessoal, obrigado. Vamos fazer uma pausa aí de uns 15, 20 minutos, depois a gente volta para a segunda parte. Fiquem à vontade de tirar foto, mas quem quiser os slides depois, é só mandar um e-mail para mim, que eu mando também os slides que eu apresentei hoje e mais o que a gente puder compartilhar hoje, tá? Obrigado. Vamos fazer uma pausazinha, depois a gente volta. com a Amelie, ou comigo mesmo, deixar meu contato aí para vocês, quem não pegou ontem, depois quiser pegar os slides que eu apresentei ontem e o material que o Ivan está apresentando hoje. Não está projetando ali. Not projecting there.
Yeah.
And you can show them the NGC container, nimo2.o, and even a demonstration of the build.nvidia.
Why don't you do 10 minutes?
I can do the build, yeah.
Why don't you do 10 minutes? Yeah.
Beleza. Vou mostrar aqui para vocês o site build.nvidia.com, que vocês podem acessar aí e testar. Né? A gente tem aqui, foi bem lembrado, meu amigo Fábio, ele lembrou da gente fazer essa demonstração do build, que você pode experimentar esses modelos Llama, Nimotron e vários outros, tá? Não só de linguagem, tem modelo aí até de previsão do tempo, né? Que a gente treina o modelo, encapsula ele num NIM, né, que a gente chama NVIDIA Inference Microservices, deixa ele prontinho para fazer deploy numa aplicação on-premise ou na nuvem. Tá? Então, aqui a gente tem alguns modelos, está vendo? O Llama 4 está aqui, o Quen, mas acho interessante. Aqui já estava ali o Llama Nimotron. Tem o Nano aqui, tá vendo, que é o pequeno, 4 bilhões. Llama Nimotron. Aqui. Esse aqui é o maior, tá? 253 bilhões. Uma coisa interessante é que ele interage em português. Alguém quer sugerir aí uma pergunta? Em português para a gente fazer para ele? Uma pergunta científica. Deixa eu fazer uma pergunta aqui. Opa! Explique Opa, tem que escrever direito, né? Explique transformada de Fourier para um aluno do segundo grau. Deixa assim. Uma das vantagens dos modelos de raciocínio é que eles lidam melhor com ambiguidades da entrada, da pergunta, do que o modelo one-shot. Ali você pode ligar ou desligar o raciocínio. Ali você vê ele raciocinando, tá? Ali ó, ele remoendo o problema, pensando. E aí a explicação. Bom, eu não estou conseguindo ler daqui, mas vamos usar aí o Supervised Fine Tuning. O que é que vocês acham da resposta? Razoável? Então, fica aí a dica para vocês usarem, experimentarem esses modelos e outros modelos. Tá? E, como eu falei, são open source, você pode usá-los para desenvolver as aplicações de vocês. Tá? E desenvolver pesquisa. Outra coisa importante é o ngc.nvidia.com, que é o nosso repositório de contextos. Né? Então, a gente tem esse repositório de container, onde, para quem já está acostumado a trabalhar com container, você tem todo o software e todas as dependências para usar aquele software, né? Por exemplo, a gente falou aqui já sobre o Nimo, né? Nimo Curator, Nimo. Então, o Nimo é open source e está lá no GitHub, você pode ver o código dele. Mas para usar o Nimo, você não precisa ir lá no GitHub, baixar, compilar, instalar. Não, tem um container pronto para usar o Nimo. É a melhor maneira de você começar a usar o Nimo. Né? Na sua máquina, você precisa de quê? Você só precisa ter a GPU, o driver da GPU atualizado, o gerenciador de container, que pode ser Docker ou Singularity, e todo o resto da pilha de software que você precisa para trabalhar com o Nimo, seja Curator, Evaluator, Customizer, está tudo empacotado, pronto aqui. Você tem um ambiente de desenvolvimento pronto para trabalhar com o Nimo. Tá? Então, era isso que eu queria falar. O modelo está disponível, o exemplo lá do build, né, que vocês podem explorar, e o pacote de software, né, que o Ivan agora vai entrar mais nos bits and bytes, vai mostrar código aqui, e saiba que quem quiser repetir isso, já tem todo um ambiente de desenvolvimento pronto, que é esse container. Tá? Obrigado. Back to you.
All right. So in the beginning, I said we're going to do this and we'll get more technical. So this is now, we've started with this use case. I gave you an overview of how to think about the application side of language model. What are the important pieces on the core of the language model itself that you need to think about. Now what I want to do is I want to do some product management kind of task. I know we are a lot of engineers and scientists here, but we have to collaborate in building application. It's not only engineers that build application, it's product managers. So I want to give you a view of how product managers and project managers are thinking about LLM applications. And maybe even if you are not a product or project manager, maybe you can give insights to your colleagues around how to sort of build a project plan to get this off the ground. So next 15, 20 minutes, again, I'm going to go through this live project that I have, and I will show you the product and project management aspect of building an LLM application. And I want to get feedback from you and questions from you around, in your own projects, how would you, change the task that I have and change the timelines and deadlines that I have that works for your project. Okay, so we will start with the user story. I will restate the user story again. The user is a citizen. It's a citizen-facing service. It's an application that is mobile device, right? So you can either talk to it, so there is ASR, automatic speech recognition, or you can type in your query in a non-English language. This is for an India customer. There are 22 official languages in India. 22 is a lot too much, so we've scoped it down to 2 languages, and I'll show you the process of scoping down. The first use case is in the water utility side. We are saying, the user says something like, oh, I have this bill that is way too high compared to the bill that I had in the last 6 months. And the assistant, or the chatbot in this case, is able to now go look up the bills. So there is a SQL query structured data retrieval that's happening. And it is able to now reason through and say, okay, this is what happened in the last few months, and this is what's happening right now. And potentially also provide some suggestions. Maybe there's a leak in your water pipes, and hence your bill is too high. Right? So it's a helpful assistant in the manner in which it can interact with the user for this particular application. Any questions on the use case itself? Do you have other use cases that are analogous? Do you have questions about this use case? Is this use case understandable? Yes. Okay. All right. So apologize. Let's see. There we go. Oh no. So I'm going to start down here. Which is literally my first conversation with the customer. Okay? This is what the state of the customer was. And I appreciate if you guys don't take pictures because this is proprietary customer stuff. I'm just sharing with you guys to give you insights around, a live project that's happening with an important customer, right? In the first project, when an engineer and a product manager and a user sit down together, and this is the recommended approach, is you have a product or project manager that you bring into the table. You have one or two users, end users, that you want to help. You bring them to the table. And you have one person who knows sufficiently about technology, you bring them to the table. And you have this conversation around what are they trying to do. That's literally the first meeting. And then as the meeting progresses, we get more right? There is a lot more sort of context and things like those that is provided. Now, the way I would so after the first meeting, the project plan starts taking shape, right? So we have a plan. In May, we do a discovery, which is we go and talk to the customers, a lot more customers. Usually, I recommend talking to 15 to 20 end users that you have and giving them unprompted sort of task. You say, okay, let's say you have a powerful AI that can help you with your water utilities. What would you ask it, right? You have this very general sort of understanding of what the user wants to do. And this is a brainstorming session where you're trying to gather user requirements. And then you do project planning. So those are the two steps that needs to be done the first 2 weeks of May. That's what we did. We went and we collected a bunch of user queries about what users were intending to ask, similar to the one that I showed you, right? Different users had different queries of different things. And that tells us the scope of the problem. Do we need to do database call? Do we need to do web searches? Do we need to look at policy documents? All of those come through in that first 20 to 30 customer interaction. One of the things engineers do, and I don't know if scientists do this as well, is we work in our own head and we imagine this is what the customer would like. This is what, if I was in my customer's shoes, this is what I would do. That's what an engineer likes to do because we don't like going and talking to people. We don't like asking questions. Okay, and that is the wrong thing to do when you're building an application. You have to go and talk to people, end users, and you have to discover what are the use cases. What is that chat that the user wants to have? You need to have 20 to 30 real chat examples from real live humans for this project to get kick-started. If you do not have that, then it becomes very, very difficult towards the end to modify that. This is where you define the scope of the project. If you do not do this well, the rest of the project will not be very successful. Then we do stakeholder alignment. This is where I get my VP and their VP to talk to each other and shake hands and have beer and things like this. Okay? This is also very important because this is what manages our funding and the velocity of the rest of the project. We start acquiring compute. Where are the compute loads located? Can we have access to them? Right? We don't need compute right away, but the acquisition of compute is the single most technical bottleneck that I've seen in almost all the projects. They want to do interesting stuff, and I tell them, you need 4 nodes, and they don't have 4 nodes for another 3 months, right? So acquisition of compute also needs to be done in conjunction as we are making the project plan. Then we move to data set creation, models, evaluation, and each of these, this is very high level, right? This is coming like literally after the first meeting is as you are thinking about how is this project going to go, you have this high level task that you write. Questions? So we start teasing out what is that task that they want to do. In this particular case, the customer wants to do two different things. There are two different work streams. One work stream is pre-training a foundational model from scratch on Hindi. It's a local language. They also added Telugu as a nice to have. So Hindi is a must have, and Telugu, the second local language, is a nice to have. So having this stretch goal helps. So we have two different work streams. One is Plan A, and they want to do a reasoning model for Hindi. Okay, this is model that is built from scratch. You need a lot of pre-training tokens. You need a lot of compute to do this. That is work stream 1. There are a bunch of team members working on that. And there is work stream 2, which is Plan B. Which is a supervised fine-tuning. You take an existing model. It could be the model that you just pre-trained, or it could be a Llama model. It could be a Gemini model that is open. And you do supervision using the token of your choice, right, for the use case in the language of your choice. So in this case, let's say you have a language model that is Llama 3.1 or Llama 7, right? And what you are trying to do is not trying to pre-train that model, not trying to change the language capability of that model or the knowledge capability of that model. All you're trying to do is focus that model so that it can do this question answering kind of thing that you saw before in Hindi. Okay? So those are the two different work streams. And each of these work streams, I will go a little bit, and then I'm sure you guys have a lot of questions in each of these. So on the dataset creation side, task 1, prepare evaluation dataset. I always start with evaluation. If you cannot evaluate what you're doing, you don't know how to measure progress, and you will not make progress, right? So prepare evaluation dataset. Task 2, deploy LLM NIM, which is what Pedro just shared. We want to use a large foundation model, like the 270B parameter model, that Llama Nemotron that we distilled from the 400 billion parameter model, or even Anthropic or OpenAI's other models that are out there. And this is to understand how do we generate synthetic data. You want to get this done as early as possible, because when you create your evaluation dataset, you will need this. The way to create evaluation dataset will require a LLM to help you to create the evaluation dataset. Task 3, create a report showcasing the current capabilities. This is baselining, right? When you go and say, I need $5 million for my compute, people are going to say, why can't you use OpenAI? Why can't you use Llama? This is saying, look, the performance in my use case, if I use Llama as it is this. This is where my customer wants to go. And that gap I can only have if I do more training. And that's why I need the compute, right? This is aligning for justification of why you can do compute. And it's also a good sort of idea to baseline. Once you have an evaluation data set, typically as you do in science, you create a baseline and you improve on that baseline. And then finally, this is a subjective report, right, where you have human evaluation. I talked about human evaluation in one of the previous slides. You also do human evaluation in terms of how good each of these open models that you could use are. How much effort do you have to put to make these open models better? What is the open model that you start making better? Is it Gemini? Is it Llama? Is it something else? Is it DeepSeek? We don't know. We have to test to understand the baseline performance of each of these models on our evaluation data set to understand what is that model that we should pick to make it better. Questions? Yes?
When you said that you're going to add the other Indic languages later,
Yes.
do you train the model in Hindi first, and then you train another model on top of it? It wasn't very clear for me.
Okay. So in work stream 1, where we are trying to pre-train a language model to be natively fluent in Hindi, in that case, we are saying we will have a data set of English and Hindi in our case, to build a model that is a Hindi model. That is the base model that we'll use for workstream 1. Workstream 2 is assuming there is a base model, either Hindi or something else, and it's saying now I need to do supervised fine-tuning for the use case that I have, which is this chatbot for utility, right? That is workstream 2. Workstream 2 can use any model. It can use a llama model, it can use a Gemma model, or it can use one of the model that is just trained on workstream 1. And what I'm saying is in both of these, baselining, right, creating a baseline for llama and Gemma and things like those is going to help you understand what is that gap that you have to engineer to overcome. Does that answer your question?
Yes, thank you.
Other questions?
Regardless of whether they use the model from plan A or they pick another model off the shelf in case plan A goes horribly wrong, do they tend to run this model on premises or are they okay with using
Excellent question. In this particular case, the customer is a government utility. The end sort of buyer of this is going to be a government. And they really, because it's a sovereign use case, they want to ensure that they have protections on data and sort of limits on compute. So they are running this on-prem, so to speak, in a NVIDIA cloud partner. So the NVIDIA cloud partner can provide you isolated environments that allows governments and other regulated entities to run the workload in those clouds without actually exposing it to the rest of the internet. Other questions? So this is workstream 1, plan A, which is pre-training. Now we need pre-training corpus. So the first thing we do is reuse what is openly available. And a data set that we have, Llama Nemotron, that data is openly available. Some of that data is openly available. So we want to reuse that data, right? And there might be data that you guys can use for your own project, at least the English data that is reusable. Now you might have to translate that, which is probably one of the steps down here, collect new sources of data, filtration, and things like those. Right? So there's a pre-training corpus, and task 5 is final processing of the data set. So at task 5, you will have a token count. And this is when people say, I have 1 trillion tokens of data. This is what they mean. When they get through to the task 1 through 5 in this pre-training corpus, what is the total data that you have left? In the case of Nepali, as I indicated, the most pre-training data that I could find is less than 1 billion tokens. Very, very small corpus. In the case of Hindi, we could find about 700 billion tokens, just raw tokens. In the case of Portuguese, I heard yesterday that some folks are trying to get to 1 trillion tokens at task 5, right? And if you have 1 trillion tokens of Portuguese, and if you have maybe another 1 trillion tokens of English, that's 2 trillion tokens. That would be pretty good training material for a small model. Once you do the pre-training, now you want to go after some of the post-training steps. So we want reasoning, right? That's one of the customer requirements. The system has to reason, once it gets input from the database, it has to reason about certain things. So in the pre-training data set, we don't put reasoning traces yet. However, after the, yes. Yes, please. Yes. Yeah, so the most recent example we have is from Llama 3.2, and I believe they use 15 trillion tokens for 15 trillion tokens, yes, for their pre-training for the 7 billion parameter model. So the Llama models, I believe, support 150 some languages, 149 or 150 languages. The long tail of the languages usually provide some language fluency, but do not have a lot of knowledge sort of thing, right? Majority of, so in the Llama case, over 80% of their token was English. In the case of Barcelona Supercomputing, when they did that model, about 50% was English, and the rest was European languages. Right. I feel there is sort of, you don't want only Portuguese token.
No, for sure, but
Yes.
if we had access to 7 trillion tokens English, and another 7 trillion tokens Portuguese, and another tail of other languages, that'd be like the need to do a language model Portuguese based.
Right. Portuguese primary sort of bilingual model, right? So iGenius in Italy is a company which is following the exact same path that you just laid out, right? Where they have, several trillion tokens of English. They have, latest count was about 2 trillion tokens of Italian, right? And they're like, again, this takes time. It's usually when you build foundation models, you have what we call a model family. You don't build one model, you build a family of models, right? And you start with small because you have small data set initially. And you grow the data set and you follow that chinchilla scaling that I showed initially in terms of increasing the size of the data set as you build newer and larger models. Right.
What would be like the optimal proportion of tokens for a balanced trilingual model?
How big is the model?
Let's say in 6-bit size, 607, 680 billion.
Yeah.
Let's say we have 20 trillion tokens,
Yeah.
and you have what, 5 trillion tokens of each,
Right.
then a tail would be something like that.
Esse exemplo que você está dando aí de espanhol com português é exatamente o projeto que o Sênia do Chile está fazendo e o professor Fábio Cosman da USP comentou ontem, né, o projeto Latam GPT. Né, o Latam GPT, a ideia é ter um corpus espanhol da América Latina e, com essa parceria com a USP, vai adicionar também português. Tá? É o que o Ivan falou, é uma jornada, né? Você começa treinando modelos menores e vai crescendo à medida que o seu corpus vai crescendo também. Até porque, quando você coloca uma aplicação, faz o deploy da aplicação, os usuários passam a ser uma fonte de token para você. Entendeu? Então, você coloca a aplicação rápido com um modelo menor, e é o que a gente chama de data flywheel, e reinforcement learning with human feedback. Mas é questão de... questão também, é aquilo que o Ivan falou no começo. Né? O dado de melhor qualidade ele é caríssimo, né? Porque você tem que fazer a curadoria manual. Sim, né? Beleza. Bom, a gente vai continuar esse debate, né?
Okay. So I have like two comments to make, right? One is data set size, total data set size is super important, but I would like, the general rule of thumb is the more data you have in the pre-training, the better, right? So I wouldn't say I have a limit. You give me more, I will take it, okay? On the post-training side, the more important part, rather than the volume, is the quality, right? In the pre-training side, that is not the case. It may or may not be the case. Okay, so there's like a subtlety, and this is something we talked about yesterday. There's out-of-distribution sort of things that you want on the pre-training side to learn very rich features. You want multiple languages, you want sort of diversity in the text and all of that on the pre-training side. And if you just use the pre-training data to build a base model, it is probably not going to do well in terms of tasks like summarization or translation, right? But the post-training, the stuff that you do here, if you do very high quality, then you need much less. To give you an example, the Llama 3.2 model, they have about 2 million chat conversation data set. In the supervised fine-tuning, the workstream 2 that they did, they have about 2 million examples. And each of those examples cost them average, $10 to $15, sort of. That's my ballpark guess of how much it would cost them to produce that, right? So there's significant amount of sort of data set curation that's happening that allows the model to perform really well on the post-training than the pre-training side. Pre-training, you want as much information that is non-duplicate as you can have. You don't want duplicates. You still want to clean the data so it's like non-duplicative. It doesn't have any, forbidden content, right? Guardrail content and things like those. So you want to filter. You might want to also filter for languages and things like those. But the larger is better for the pre-training side. And then post-training, we have this ability to tune the model with high-quality data set.
Last question.
Yes, please.
It's better to start trilingual, or it's okay to start bilingual and tech a third language? Because it's a question of strategy, right? If you can start with Portuguese, English, and then try to annex Spanish, or you'd better to just start with trilingual Portuguese, Spanish, and English? Does it matter? It is important from a strategic point of view?
Well, in this project it does. And the reason it does in this project, it increases risk, right? The second language that they want to do. So they want to do English because English is also an official language of India. Hindi is the most populous, like this language that's spoken by the most people. So that's the second language that they want to do. The third language that they want to do is Telugu. Right? And that Telugu increases project risk significantly because the data set in that is really small. Like I'm going to have to deal with really small data sets. And the annotators are also not there, right? I don't have human annotators to give me highly curated post-training data set. So in that particular case, in my use case, Telugu is like we deprioritize the third language for strategic reasons because it increases project risk. From a sort of learning point of view, the implication is just class balance. If you have, right, let's say you have English that is, half the tokens, Hindi that is, another, 30%, and you have Telugu that's 20%. That class imbalance is going to show up in the use case, where, when you have the evaluation in Hindi, you get higher score than in Telugu for the same, very similar type of use cases. Yeah, it depends on the use case, right? Like I would first define what is the first use case that you want to build, right? And let's say you have these, use cases fairly well defined. You can define how much tokens you need for good language fluency. In the case of electric utilities that we are doing, we don't need it to understand literature and science and all of those, right? So the kind of tokens that we need is fairly limited, and we're gonna select those tokens in the post-training side. We're not going to filter those tokens in the pre-training side. We're going to put in everything because we want that out-of-distribution stuff. And the post-training side, we're going to filter it to say, okay, I'm not going to give you any medical stuff. I'm not going to give you other stuff. I'm just going to focus on the utility aspect. So use case really drives this. Other questions? All right. Yesterday we talked briefly about tokenization. The plan that we have for tokenizer is we want to update the tokenizer that exists for Llama Nemotron, which is the base model in our case, to also support Hindi. Okay, that's sort of a minimal change we can make. We want to support the extension of the tokenizer, right, which is a little bit harder task. So there's task one, which is just taking the existing tokenizer and updating its weight so it's more biased towards Hindi tokens. Again, in the sort of token space, if you look at the vector, there's already Devanagari script, which is the script for Hindi, in the original token for Llama Nemotron. Llama will understand Devanagari. It can respond similar to what Pedro showed for Portuguese. If I ask that Llama model something in Hindi, it will respond back in Hindi. So it understands those tokens. There's already a vector space for that token. What we need to do is give that vector a higher weight compared to other vectors. For example, Spanish or French or other things, we want to give Hindi a higher weight. So there is one mechanism. Task one is just to update it. That's the simplest way. We get some benefit out of doing this, so that's what we do. If we have time and we are more ambitious, we can extend the tokenizer to append something else, the sort of things that a Llama model may not have seen before. And that is a separate thing that we can append to the existing tokenizer. And that's a little bit more involved. It has, it has some tuning to do, but that gives much better performance. The third option would be when you're pre-training, you can also train a brand new tokenizer with the pre-training corpus that you have. If you have trillions of tokens, why rely on tokenizer that others have produced? Why not build your own tokenizer from the ground up that is more aligned to the data that you have? That is the most expensive and most risky option. Because if the tokenizer is not good, and there are difficult ways of measuring the performance of a tokenizer, if the tokenizer is not good, then your language sort of model building at the later stages, when they fail, you don't know if it failed because of the lack of tokenization performance or because of something else. So there are multiple levels of how you can think about tokenizer. The lowest cost one is what we're going to go here. Again, as an application developer, my goal is to reduce risk for the whole project. And the way to reduce risk is just tack on to things that already exist. Don't try to do new things. Questions? Yes?
In the first part of the presentation, you mentioned that the tokenizer, if you actually do master it, is usually the last thing to do, right?
Yes.
If you break the tokenizer, let's say, how would that manifest in the model? Would you write nonsensical sentences? Would it hallucinate? How?
Yeah, so typically what I've seen is it will start mixing languages in a non-intuitive way, right? So it will start sort of sentence in Portuguese, and then it's going to insert some English or whatever the secondary language is, and it's going to continue in Portuguese, right? Now, that sort of sequence of mixing of languages might exist in the training data set, right? But when you mess with the tokenizer, those features might just spike up. The thing that I've seen, and the only anecdotal evidence I have this is with a Thai model. They fine-tuned a tokenizer, they extended a tokenizer on Thai, the Llama tokenizer on Thai. And what they found was there's this mix of languages on the output side. Again, there are ways to mitigate it. It's a little bit more involved effort. Changing tokenizer is a complex, involved effort. How would we evaluate this, right? So we talked about creating evaluation as the first step, right? What are the things we need to do? Well, in our case, we have reasoning is a main feature, right? So we want to create a reasoning benchmark. And we want to do this with the cheapest way, again, reduce project risk by translation. We have reasoning data sets in English. In fact, NVIDIA has an open source reasoning data set. You can go to Hugging Face, look at it. You can use a language translator, either a LLM or a specific translator, to translate that reasoning data set into a Hindi translated reasoning data set. Now, there are complications with translation. One of the complications with translation is most translators that exist today are sentence translators, right? What that means is they work at a sentence level. In most tasks, as you can see in the use case that I have, there will be multiple sentences in the conversation. And what happens when you do sentence translation is you lose coherence across sentences. So let's say I have a 5-sentence response from the agent that is in English, and I want to convert to Hindi. The tone of the first sentence might change to the tone of the last sentence in that chat conversation, even though it's in the same paragraph of text, because the way I'm going to translate is sentence at a time. LLMs don't have this problem. If you use an LLM to do translation, if you use a Llama model, right, again, you need a significantly large model to do translation. It needs language fluency. If you use a large model, then it will do translation very well because it can translate a whole paragraph. And sometimes I've seen a whole chat context. 15, 20 conversation turns is translated by these large models into target language. Translations have another sort of issue, which is the quality can degrade and it needs human supervision. So the reason I said for evaluation you need to stand up this inference endpoint, the NIMs, is when you are creating this through translation, you create this, maybe you have a few thousand of these, and then you have a human or ideally 3 humans scoring each of these, and you average the score of the 3 humans to get an evaluation that looks good. Questions? Yes, please.
So on the example we saw a little bit before where it was on NVIDIA's website, the reasoning was in English and the answer was in Portuguese.
Yes.
Is there a reason for me to expect a worse response in Portuguese because the reasoning was in English? What I'm asking is basically,
yes.
Let's say I'm using any model in my home. Should I expect an answer for the exact same prompt in Portuguese or in English? But the reasoning is in English. Should I expect the English answer to be better?
If you don't have a Portuguese reasoning data set, the answer is yes.
Okay.
So typically the way, at least DeepSeek's data set, right, the way these and everybody else follows now what the recipe that they have, is for multilingual reasoning tasks, they have, a specific step in which the model recognizes that the user has asked question in a specific language, and in the sort of alignment, the post-training phase, they ensure that the responses is in the original language. So it's an alignment rather than a knowledge capability of the system, if that makes sense, right?
Yeah.
So it's essentially doing it's thinking in English and doing translation. If you had a translated reasoning data set in Portuguese, then it would think in Portuguese. And a lot of sort of anecdotal evidence that I have is if you reason in English, the things that you'll miss is cultural artifacts. When I say, I want to buy a red wedding dress, okay? Just think about it. You say, I want to buy a wedding dress, okay? And suggest me some, shoes to go with it, okay? The language model that is trained only on English reasoning data set will assume that the dress that you're buying is white, okay? Because majority of the tokens that you have seen has that cultural context of white wedding dress. However, in Nepal and India, people wear bright red colored dress when they go to a wedding. And that nuance, that cultural nuance will not come through if you do not have a reasoning data set in Hindi. Does that make sense?
Yes. So basically, for example, if I'm coding something, it's probably better to ask it in English to a model that reasons in English, since we have more code data set available in English, right? If I were to ask it in Portuguese, for example, since the data set won't be as large.
In a general sense, that is true. The sort of caveat that I have is model size, right? We know from some of the charts that I showed you earlier, as the model size increases, the capability of this language model also increases. In the community, we call this emergent behavior, right? As you increase the model size, previously it was not able to do translation. Now it is able to do translation. Previously it was not able to do reasoning. Now it's like, so as the model size increases, the language fluency increases with it. So you might not have that issue with a really large model, but you will have that issue with a smaller model.
Thank you.
Yep. Other questions?
Does that relate to sort of the main one as well? If you have a post-training, say, or if you could find a way actually to get a model that was trained for, say, solving mathematical problems, and then ask it to translate text from a language to another, would it break in a catastrophic way?
Yeah, math specifically is very hard because they are not non-English words or non-Latin words, I should say, right, that are representative for a lot of math in other languages. Like in Hindi and Nepali, like, you know, theorem is a theorem. It's still an English word, right? We write it with a Nepali script, but still an English word. So I feel the data set itself, right, the knowledge capability, if I just train on that particular language, it may not have that math capability at all just because it hasn't seen that token. That's why my recommendation is like at least 50% has to be English because you don't want to lose on the knowledge capability by just focusing on the language fluency part.
But you would do that in the post-training phase or the pre-training phase? Would you focus on the specific domain that you want to have?
I would say in the case of this guy, right, the stuff that we are doing on the utility side, the pre-training phase doesn't have any domain-specific data. The pre-training phase is just for language fluency and just general knowledge. On the post-training is when we focus that to both, you know, to talk in a particular tone, which is colloquial language, right, which is different than what we find in the internet, and then also for that use case. So talk in that colloquial term for that use case is the post-training side.
But then you have a case where the post-training data was completely unrelated to the pre-training data, no?
The hope is there is intersection, right? The pre-training data is so large, let's say trillion tokens, there is enough intersection about water utilities and, you know, leakage in pipes and, you know, things that are related to it, right? That's the hope. Now, that's not true in some cases, right? In science, for example, that's not like chemistry, physics, right? That's not true. It's not true in finance, right? There's, you know, Islamic finance law is very different than, you know, other sort of laws that we have seen, right? So there's very domain-specific training, and that can come in pre-training. I think it will also come in pre-training, but majority of that is going to be post-training.
Then you would say that is that a requirement? So if you have a very specific domain knowledge, you would have to take a part of that data set and also use it in pre-training.
Absolutely. I have seen people even include post-training data in pre-training. At the final stages of pre-training, I have seen people use reasoning data set and things like this that typically is not in pre-training data at all. And that seems to bias the model to do better in performance, like use case performance. Yes.
You can see our playbooks for PAPT, like
Yes.
the chip Nemo that we
Yes.
use internally.
Yeah, so domain-specific application, we have a bunch of domain-specific application within NVIDIA. One is around, you know, coding for chip design, right? We call this chip Nemo. And essentially, it needs to understand the vocabulary that the engineers use so that it can be a co-pilot to these engineers. And for that, we not only did post-training, we also had to do pre-training on all the, you know, millions of lines of code that NVIDIA has written over the years. Because some of the VLSI sort of code is so specific to that domain that the token distribution in the internet is very small, right? You don't get like 10 million lines of VLSI code in the internet. And if you want to teach a system to do well in writing VLSI code, then you need to have that data both in the pre-training and also on the post-training side. So I think we had like 24 billion tokens on the pre-training side in addition to the regular tokens just to focus on chip design. Yes? Yes. Might. Again, like the chip Numa project is not open, right? We don't like. show how others should build chips. But the paper is there. We have academic paper discussing what are the different trade-offs and things like those. But you can follow the same recipe. And I will show you one of the ways you can follow the recipe very quickly, right? And that will get you to that point of being able to specify what is the domain and what are the pre-training, post-training steps you need to do. All right, work stream 2. So this one is, again, we assume in work stream 2 that there is already a base model that is fluent in the language and has the knowledge capability, right? That's the assumption we're going to make. And then now we are going to take this model that's already language fluent and knowledge capable and then make it so that it will work well for that task. So it starts with evaluation, right? We have a small static data set that's coming out in June. In fact, we have 4,000 examples in this data set already. This is created synthetically by basing on examples from real human interaction. So remember at the beginning I said first you need to do a project plan, you need to invite 20 users to get their interaction documented. You use the 20 users as few short examples and create new examples using LLM and you scale that. So we went from 20 to 400 and a human evaluated each of those 400. We had linguists come and evaluate those 400 examples and make sure in each of the evaluation axes we were performing well. Is it colloquial language? Yes. How much, right? Give it a score of 1 to 5. So there are 3 raters for every chat conversation, single turn chat conversation, and they have to rate one chat conversation as being 1 to 5 in language fluency. Okay? And you have 3 raters and you do an average of the score. And you do that to go from 20 to 400. 20 are human, 400 is synthetic, but human has looked at those 400 to make sure they are good quality. And then you do the same step again. You go from 400 to 4,000, right? There is this mechanics in which you tell the language model, hey, this is what I'm trying to do. We call that a few shot example. If you tell the language model, this is the way the chat conversation is going to go, and put that in the context of the language model, it will be able to do that task better. So in the synthetic data creation side, we put in 5 different examples of conversation, and then we ask it to produce the next conversation. That way, we have some real human data or some validated data in the input, and then the LLM produces an output, and the human evaluates the output whether it is good or not. So it's an iterative process in creating this evaluation data set. We start on a small static data set in June. We do negative mining and scale. Negative mining essentially is when you generate a lot of synthetic examples, some of them are going to be really good, some of them are going to be really bad, some of them are going to be true positives, some of them are going to be false positives. And negative mining is an idea where if it is a false positive, then it's really important to put that, correct that and put it back in the data set, right? That's sort of the idea is you make the data set richer by investing human resources into it. The more humans look at it and give feedback, the richer the evaluation data set becomes. And that's sort of what we are trying to do here. And we do human evaluation, the most expensive part, with real users in August. Right? So if you look at month by month, we have like a 3-month cadence, and in 3 months, we want to get to a point where we can do user studies of the application end to end. And that would be the human evaluation. The evaluation data set, the way we're going to do this is a single turn, right? So the user asks a question, the bot responds, that's a single turn. So each rater, each evaluator is going to look at one of these turns and give a score of 1 to 5 in one axis or multiple axes. We do 5 turns to make sure the coherence in the conversation is going so that it's not going in a random direction. So you want to make sure you take a random 5-turn window from your chat history or whatever, and then you evaluate, turn that into evaluation. And then you do a full session evaluation where the user logs in and then the user logs out, and you can evaluate each of those steps. So these are the different ways you can create evaluation data sets A lot of this is synthetic, as I said before, but there is this loop where the human goes and curates the synthetic data set to come up with higher and higher quality evaluation data set. To me, when you start a project building an application, even a 20 question, 30 question data set is good enough to get you started. But quickly you want to use the synthetic methodology I described to get to 100, few hundred, so that you have fairly good idea of the different axes of evaluation and how things are performing. Ideally, you would want to get to thousands or even tens of thousands. For companies like Meta, they have evaluation data sets that go in tens of thousands of examples in each of these axes. And sort of this is the overall plan, right? Now, how do I take this to the customer? Now the customer has to actually execute it, right? So this is a plan. This is in my head. We've talked among engineers and product managers. Now this gets translated right into a specific task that has there you go. That has a list of tasks, description, who is going to own it, who does what is the status, what needs to be done, right? I am showing you a non-updated version of this, but the idea is you create that Word document or a project plan without thinking about deadlines and constraints and who is going to work on it in sort of isolation. And then you figure out, okay, what is the resourcing of this? How do you execute this? And you create a detailed plan like this. I'm sure you guys have seen many variations of this. But the idea is we want to go step by step and tackle more and more complex things. And lastly, I'm going to share with you guys this particular package. So this is something that I've been working on and a bunch of us have been working on. Pedro has been also involved in figuring out how do we enable very quick development on the use cases that I just showed you. If you wanted to get things done, let's say you have a task and you wanted to get an application out by October, which is the task that I was given, how would you do it? What is the code that allows you to do it? We are using NeMo, the NVIDIA framework for doing language models, but we are repackaging some of the NeMo so that it's very specific to this use case development for LLM applications, both for workstream 1, which was pre-training side, and then also workstream 2, which is the SFT side. So in this particular case, I'm going to go through a couple of these things to show you how it works and how extensible and easy it is for you to use. But this is a repository. It is right now, I don't have a license, I believe, but I believe it is going to be an MIT license at some point. It is not new code that we are writing. It's not IP that we are writing. We are taking NVIDIA code from blog posts and from other sources, and we are repackaging and we are testing it so that it works for non-English language modeling. All the sort of blog posts and NVIDIA artifacts that we have, they are guaranteed to work in English, right? That's sort of how they have been developed. But we haven't extensively tested it for low resource language, and this is an effort for us to test it and make sure that the code that we are writing works for non-English languages to build both of the work streams that I talked about. Okay? So by show of hands, how many of you use dev containers? Okay, all right. So one of the things, right, let's say you are now a product manager and you are trying to have a high velocity for this project. You want this project to go fast. The way you're going to think about this is what is the development environment for my engineers? Okay, typically in academic labs and also in scientific computing, what we've seen is there are experts who will do everything by themselves from scratch because they know how to do it and they have very specific sort of methodology and it works for them and it's perfect and they don't want to change it. That's fantastic. However, the AI sort of field is moving so fast, it's very difficult to have a consistent sort of work environment. Dev Container is a programming environment developed by Microsoft, and it works with VS Code. It's an editor, a code editor, and it gives you a consistent development environment based on container technology, Docker containers, that you can port across different machines. So if you use a dev container in machine A and you build some code over there, the same experience you can have in machine B without changing any of your development stuff, because all the development environment is captured in a container. Does that make sense? So it's a container environment that allows you to have a consistent development environment across the whole project, across team members and across different people in the organization. It is fairly straightforward to set up, and we've already set it up so that it works well for Nemo. There's this JSON file, and it relies on a Docker Compose, which essentially is a mechanism of orchestrating multiple containers together. And it connects with your remote machine, or if you're doing a desktop development, it connects with the GPU in your local machine, so you can do work from inside the VS Code environment. You don't have to go outside the VS Code environment to get any of your work done. It will automatically detect the GPU, it will load up the Nemo, and then if you type in a command, it's just going to execute on the GPU. That's the advantage of Dev Container. It just makes it easy for you to get started very quickly. And I'm sorry, I'll keep on losing my cursor. I apologize. I did say I was going to share code at the end of the presentation, and this is the code. So the way the container is going to work is it's going to spin up a bunch of services for you. One of the services it spins up is for doing your synthetic data generation, right? So we are going to use a 3.2 billion instruct model as a NIM to create synthetic data. Now, obviously, if you have a small GPU, that's what you want to do. It's not going to fit a 70B parameter model. However, as I explained before, if you want really high-quality, non-English language synthetic data, you want to use the largest model you can afford. So this, you can change the NIM if you have a large model, and when you reboot this container, it will automatically get that larger model from ngc.com. It will download it, and you can start inferencing and generating synthetic data automatically. And this is how it will look like, right? So once you git clone this repository that I was sharing with you before, you can start up either in VS Code. This is a variant of VS Code called Cursor. It allows you to automatically write a bunch of LLM code, right? And it will just pop up. And this environment is already ready to go in terms of LLM toolkits and everything. Anything that you need from NVIDIA for language modeling is already included in this development environment. There is no installation that you have to do. There is no package management. There is no driver configuration that you have to do. It just works out of the box. And that's sort of the big advantage here, is that it works out of the box. I'm going to give you a quick overview of this, and folks that are interested, please contact me or Pedro, and then we'll give you access to this code so you can get up and running very quickly for your own projects. So we have scripts to allow you to start collecting data very quickly, right? So we have the acquired data script. I believe we have ability to download Wikipedia. So if you have not downloaded Wikipedia Portuguese, you can do that. You can download all of Wikipedia. We have Red Pajamas, which is a curated set of internet data that you can download. Both of these are free, obviously. You can download and you can test this system very quickly by downloading, let's say, a small quantity of Wikipedia data. And then you can do things like deduping, which is removing all the duplicates in the data. Normally, when you want to download, let's say, 10 trillion tokens, the way you do it is there is a nonprofit in the US called Common Crawl Foundation. They produce this big data set, which is a collection of all the internet files that they can find, and they dump it in one big place. It's called a crawl dump. Every 3 or so months, they do this, and each of these can be in terabytes. Now, every 3 months, the internet doesn't change so much, right? There might be 2%, 3% changes to the internet every 3 months. So what you have to do is remove all the duplicates, and there is a script that removes the duplicates, which is the dedupe script. There is NVIDIA download SFT data, which allows you to download the open data from NVIDIA. So you can get started, and if you wanted to convert this into Portuguese, we have a translation mechanism down here, right? So we have a bunch of things around translation. And I can't seem to scroll down here. So we have translation from one language to another to test out your language model as you are building it. We have a live chat that you can use with your local language model as you are building it, so you can chat with the model to understand, to do some anecdotal testing. And then we have evaluation as well. There are a bunch of other things here, but this thing will get you started very quickly. You can start getting, some tokens downloaded. You can start doing some pre-training. You can get a feel for what is it that is required to make this work. Now, to really do this at production scale, you cannot do this in a single GPU or even a single node. You need multiple nodes. You need large enough storage, right? You are talking about tens of terabytes of data and filtering through tens of terabytes of data. So in plan A for the customer, they're going to acquire 64 nodes and consume, commercial, storage to use this script to download a lot of data and then filter them to curate that, trillion token data set that they need. And once that trillion token data set is there, then you create, your alignment data, the use case data in the manner that I described before, which should be down here somewhere. All right, so there's evaluation and there's a bunch of translation of the data. What is coming in this package very soon is we will have ability for you to pre-train. That's already in the MR. We will have ability for you to fine-tune. So the use case that I shared with you on the Nepali sort of electricity, the water utility use case, that is going to be supported by this within this month. Well, next few days, I guess. So from that point of view, this is in rapid development. I would love for collaborators here to run with us as we build this. I would love to get 1 or 2 more collaborators to get better product feedback for myself as I'm building this. And my hope is this will really accelerate the application that you're building. So with that, let me take more questions. Yes.
So I have 2 questions, actually. One is from a little bit before. You talked about few shot, right?
Yes.
I was wondering, we were reading an article recently for a class that I'm taking that talks about few shot. And do you think it makes sense to use few shot approach not only into the data set training, but could I use kind of like in a reverse order? Would it make sense for me to use a few shot approach on prompting? So basically, giving the model a large model, right? A well-structured prompt, but with, I don't know, about 10 or 20 well-working examples. Does that make any sense?
Yeah, so I mean, that's the right way to do it, right? So the way I think about language models, right, is the context of the language model, the input context, the place where you put the input, that is your working buffer, right? It's almost like an L1 registry for the language model. The more information you can pack in that context window, the better sort of structure of information you can pack in that context window, the better output you should expect. So from that point of view, showing it examples of this is what I want you to do. For example, in translation, if I put in translation example, when I give you an English sentence, this is the Nepali sentence I expect back. And if I do that 5 times, the language model will understand that pattern of what is it that I'm asking it to do. Few shot examples are very powerful. I use it all the time. Even in this repo, we have a bunch of few shot examples. The way to sort of make them more effective is if you can select your few shot example that is very specific to the thing that you're looking for, then it becomes even more performant. I'll give you one example. I was working on, I can show you something, but I was working on text to SQL about 6 months ago, right? And when you go from text to SQL through a language model, you ask it a natural language query and you want it to produce SQL code that you can run. In that case, the improvement because of few shot learning was almost 30%, right? If I did not give few shot learning sort of examples, then the performance degradation was significant versus if I gave it few shot example. And if I wanted to get even higher performance, then I would need to give it very relevant few shot example. For example, if I knew that my database query would require a join, then I would give few shot example with a join in it so that it would have that in its context window. Does that make sense?
Yeah, so basically I need to give as many examples as I can, but also those examples have to be as specific as possible, right?
As close to the sort of task you are giving the system as possible.
Yeah.
Now
okay.
the flip side of that is you have limitation on the context window.
Yeah.
If you go back to the translation chart that I showed in my second slide, there's this performance drop that you get after a certain length of sentence, right? And that performance drop is consistent. All the models seem to perform okay until that performance drop starts happening. So from that point of view, your context length is also a very valuable resource. You don't have unlimited registers in your devices, right? So you have to manage those contexts very well. What I've found in practice is the newer models, the models that have come out in the last 3 or so months, they are pretty good managing context 20 to 30K tokens. I don't trust the needle in the haystack kind of argument. That might be useful in some use cases. But in generating synthetic data, I would recommend not stuffing your context window with a lot of text, right? I would keep the prompt precise. I would put in a bunch of few shot example. If you can manage all of that within 10,000 tokens, that's probably the best result.
Okay, thank you. And the other question is, can I run, I have a 5070, 12 gigs. Will I be able to run Nemo on my machine, or
Yes, so the Nemo framework will run if you have a GPU. The question for you is going to be, what kind of model can you run in your GPU to do any
I
sort of
presume
inference?
small models, right?
Right.
Since
So the
only
small
12
model, the 3 billion model will probably fit, right? It's or a quantized version of that would definitely fit.
Yeah, okay, thank you.
Yep. Other questions? Yes.
You said that you prefer to keep your prompts short and precise, and to keep below 10,000 tokens, you're correct?
Right.
So,
10,000 tokens, yes.
Yeah. What are your thoughts on people pushing the context lengths like to 1 million, 2 millions, so you can simply dump, for example, entire code based on the model prompt and say refactor or discuss the code base or whatever. Because like this is a active research topic right now.
Yes.
Like pushing to these really large context windows.
Yes. It is improving, right? So last year, if you asked me, I would recommend staying within 2K context length. Even with a 32 context length ChatGPT 4.0 that was there, the performance drop after 2K was significant. Now these models are now getting trained with synthetic data. What that means is they are getting trained on longer and longer contexts. Not a million, right? 32K is probably the longest that I've seen in which as an input to the model. So I'm fairly confident that if your input output is within 32K window, then the model performance will stay high. Now, the really long sort of million context window, those are useful for RAG type application, retrieval augmented generation type application, where needle in the haystack becomes really important. You want to find a fact, it is stuck in one sentence among millions of sentences, you want to get that sentence. That's fairly good, and it does well. However, that performance really doesn't translate to things like knowledge, right? The retrieval task is, it's good, it's measured, good performance, useful for that. But if I'm doing knowledge tasks like, translation, generating novel sort of examples and things like those, that long context window is going to hurt me. It's, again, like from a token distribution point of view, a statistical point of view, right? If you think about the cumulative probability distribution of the neural network for every token, the longer the context window, the cumulative probability of the next token is going to be harder to predict. Yes?
So first of all, thank you for the hands-on stuff. It's been very useful for put their hands on.
Yes.
So my question is not related to few shots, but actually another point. In the reasoning era, it still makes sense to use things like chain of thoughts in our own prompts, or it's better to leave the model to do the task that we would do in the past.
If you are, if it's single shot, right? If you're not fine-tuning the model in any way, I think it's still beneficial to guide the model to think in a certain way. Right? Chain of thought is useful in certain linear thought process, right? Otherwise, a tree of thought is sort of...
Okay, I mean, all those chains of...
Yes. Yeah, so the context management, the reasoning models do pretty well, right? A chain of thought is a context management. There are other context management techniques. Reasoning models do pretty well, and they want to manage their own context. I have seen performance degradation if you try to manage the reasoning models, reasoning too much. In fact, in the synthetic data that I'm going to show you here, I have turned reasoning off because I have found, again, anecdotally, that when I want to do things like translation, if I turn reasoning on, it does not do as well. Okay. I don't know why, but it doesn't.
That's the problem. Nobody knows exactly.
Yes. But I think the way I would think about this is, let me actually show you a prompt, right? That might be a good thing to go over. Yeah, we can look at one of these evaluations. Right? So this is a way you would evaluate. This is a prompt to evaluate a performance or performance of a particular term. Okay, I talked about evaluating turn-by-turn conversation, and this is a way to evaluate that. This is a method called LLM as a judge. When it first came out, I thought it was the worst thing in the world, right? How can you use an LLM to judge an LLM? It's like, just doesn't make sense. But now I've given up, and I'm like, this is probably the only way we can do this, because there are going to be millions of examples we need to evaluate, and we need automation. So I've come around to using LLM as a judge, and this is one way, faith evaluation. You can read multiple papers about this. Essentially, faith it's an acronym for fluency, accuracy, idiomaticity, terminology, handling of format, right? So why are these axes relevant? this is what the researchers decided to do. These may or may not be relevant to your use case. So that's sort of why I said, once you figure out what your use case is and once you have the user input, you need to define your own axis. But this is how a prompt looks like, right? You are a world-renowned professor, okay? Let me explain why you are a world-renowned professor is important, right? Because, again, you want to bias the model to thinking that it is smart. If I put in a prompt saying, you are an undergrad, entry-level undergrad, the fifth evaluation scores would not be very good. Okay? It's just, yeah.
Can you use it to become a number?
Say again?
You can use the model to become number?
Yes. So essentially, again, like think about this as registers, right? In one of the registers of the machine, I'm saying you are an expert in something.
Yeah.
And
I always start my prompt, you are an expert of Python coding, you are an expert in math, you are an expert in
So you need to coach the model to
prompt engineering.
So you need to do like a pep talk to the model?
yeah,
It's not coaching, it's prompt engineering.
yes. Yeah. So, and this is a simple, in my mind, this is a very simple prompt. And the way I make this prompt effective is I give it few short examples. Okay, so I have told it, it needs to score from 1 to 5 for every chat conversation that I give it across this axis. And for it to perform well, if I give it a conversation and a score across this axis, that is one shot. That's a one-shot example case. If I give 2 examples like that, it's a 2-shot. Few shot typically means 3 to 5, depending on the context window. But the idea is you have a simple prompt, and then you pack your context window with examples of the task that you want to do. Questions? Okay. We good? All right. So my request to you guys is please think about the use case that you're working on or you have, and let's think about how we can collaborate. This is a code base that I am willing to work with you to put in your feature. In fact, if I go over here and we have LNCC here. Okay. Enable download and filter for MC4 and Oscar DOMs. We had a conversation a couple of weeks ago, and we talked about, okay, how do we start collecting Portuguese data? And this is MC4 and Oscar are curated data sets that we can download and we can filter for Portuguese. Right? If I have you as a user of this, I can imagine there's going to be a line item that you tell me, hey, this is not working for me. I need to do this. Can you help me do this? And I can create an issue that our engineers can go and look at. If there are solutions that already exist, I can point you to that solution. If the solution doesn't exist, I can work with you and build that solution in conjunction with you. Sovereign AI is a very high priority for NVIDIA, and we need to run fast. And I want to have people who want to run with us. Thank you.
Bom, alguma última pergunta, o último comentário? Estamos fechando com 10 minutos de adianto, né, o tutorial. Antes de mais nada, eu quero fazer justiça ao que eu esqueci de falar ontem, agradecer ao nosso amigo do comitê técnico que não está presente aqui, professor Fábio Porto, né, por todo o incentivo e pelo empenho aí na organização do conteúdo técnico, que eu espero que vocês tenham aproveitado tanto o dia de ontem como o dia de hoje. Espero que saiam daqui com algumas perguntas resolvidas, mas como todo bom cientista, com mais perguntas novas, né? Então, é uma área muito nova, que avança muito rápido, e o papel, né, da academia aí é fundamental para, eu não diria controlar, mas para entender a tecnologia e entender como a gente pode aplicar ela para o nosso bem, né? É o lema do PIBIA, né? IA para o bem de todos, né? E a NVIDIA, com várias coisas que a gente falou aqui, trabalha muito na intenção de democratizar a inteligência artificial. Você vê toda a nossa parte de software gratuita, open source, a gente vem, ajuda em projetos, ajuda em seminários, da maneira que for possível, né? Fazer justiça também ao André Rafael, do MCTI, né? Que grande incentivador aí também do seminário, não pôde estar aqui porque o filhinho dele nasceu, e desde o começo da organização ele falava, pô, meu filho vai nascer bem na época, não deu outra. Então ele teve 2 filhos aí, um é o seminário e o outro que nasceu semana passada. Tá? Mais uma vez, agradecer a todos vocês, né, por terem vindo, a todos que colaboraram ontem e hoje. Foi fantástico a interação aí hoje com o nosso amigo Ivan. Thank you, Ivan, again. Eu vou passar aí a palavra final para o meu amigo Ricardo, aí, também do Comitê Técnico. Obrigado, pessoal. Outra coisa, se vocês puderem contactar a gente, a Amelie, com feedback, sugestões de como a gente pode continuar, né, interagindo, criando essa comunidade de LLM do Brasil, né, ideias de como a gente pode interagir e avançar, né, e realizar o plano que a gente almeja. Tá? Então, por favor, deem feedback para a gente de como a gente pode avançar. Tá bom? Ricardo.
Obrigado, Pedro. Ivan, obrigado. Eu acho que nem o senhor, né, Pedro, imaginava, né, a presença de tão estudantes brilhantes, né, e essas inquietações que eles trazem, né, as perguntas incríveis, né. Então, obrigado pela presença de vocês. Muitos de vocês talvez estariam em aula agora e estão aqui, mas eu acho que isso é o momento, né, de compartilharmos, né. Obrigado a toda a equipe da NVIDIA, os meninos e quem...
Agradeço ao nosso patrocinador.
A nossa patrocinação. Então, obrigado por tudo, LDA, pela presença, por todos os meninos que estavam por trás de tudo isso, no coffee break, tudo é um processo que acontece. Então, obrigado mais uma vez. E nesse momento, para celebrar o fechamento, eu vou pedir uma quebra de protocolo a vocês, que a gente se proceda aqui na frente. Nós temos ainda 5 minutos para nós batermos uma foto final e coroarmos esse fechamento. Então, pode deixar seus materiais na mesa e aí a gente se encontra aqui. Obrigado.